Hello, I see there is nobody left. I wonder why. I think it's going to be a good presentation, so stay, don't leave. I don't want to be alone. Here we are going to talk about accelerating WebKit application. And what I'm going to try to do is share a bit of what I do as my daily job, which is making WebKit faster and also making sure the application built on top of WebKit are fast enough. So who am I if you weren't there in the previous presentation? I mean, was there anybody not in the previous presentation? Cool, I'll skip that one. So as the previous one, this presentation is done with HTML5. It is just a plain web page. And my slides are just div elements. So it is again useful to show you the content directly in the slides. So this is the agenda of this presentation. We're going to start by looking into what is new in Qt 4.7 regarding WebKit performance. I'm going to skip what we improved in Qt and that improved WebKit performance. Then I'm going to spend some time showing new way of presenting web pages, new way of showing web content, and this is in particular important for touch interface, and it can be important for other use cases like TV or. Actually, most of the use cases where you don't have a mouse, you probably want this kind of differentiation. Then we're going to see how to use the graphic hardware. We're going to dive into accelerated compositing of WebKit. And we're going to end by providing WebKit and see, so you can learn some of WebKit, how it works, and hopefully find the problem in your applications. So let's start with what we changed in 4.7 and why we changed 4.7 for performance. So why you might have heard a lot about performance. It was in the factor crop. We have marketing going crazy about how fast we are now. And you might wonder why we spend so much time on performance, why it is so important for us. What happened since last year is that QtWebKit have been used by a lot more people and for a lot more things than before. With Qt 4.6 and previously, QtWebKit was used for some hybrid application, and people were also integrating web inside their application. But we did not have many users for web applications, for very dynamic applications. And that changed radically. Now we have the Qt Web Runtime, which is a runtime on top of WebKit. People inside Nokia are doing lots of application, very dynamic, and they want great performance with the Qt Web Runtime. So we had to improve WebKit. You have the OviStore on the N8. If you've played with the N8 and you play with the OviStore, it is a web application. It's not a native application, and it's very fast. It's very responsive. We had to make some changes to WebKit. We have to improve to get there. And that means that you can get like 60 frames per second on this kind of hardware. KDE integrates QtWebKit now, which is, not important from business level, let's say, but it's important for us because we start using QtWebKit more on day-to-day basis, and that's also a driver for changes. And nowadays, we do even slides with WebKit, and we don't want to look bad in front of the people, so we make sure everything is fast. So to get there, to get from 4.6 to 4.7, we had to change WebKit all over the place. We had to improve Qt. And I can say the complete team in Oslo worked on performance at some point. Everybody worked on some little stuff, and it's the accumulation of all these little changes that make the performance of WebKit as we have it today. I focus here on some features that have been added in 4.7, like you have the accelerated compositing path in QtWebKit. This is taking advantages of the CPU, of the GPU, to do some operations. So now that you have the GPU and the CPU, you have way more power to do operations, and that can give great performance if you have the right use case for it. We are going to dive into that later. We have more mobile based option, what I mentioned previously, like the touch, what you don't render with a mouse. And when you have that, that enables new optimization, new kind of optimizations. And we have better caching of web pages. And I'm talking about caching of the rendering, so you can get very fast rendering. And so this is called tiling. We are going to see a bit of that. And we have better models of rendering, which make tiling so effective. And yeah, you can think of caching differently when you present pages differently than today. We also fine-tune the rendering to get as much as we can out of every CPU cycle. So we got, for example, smarter update region, because when you do an update on a part of the page, you have to re-render this part, and that means re-rendering, finding the value of each pixel in this render area, and finding the value of the pixels, doing the blending takes time, is CPU intensive. So what we did is improve WebKit to update as little as we can when you have an update. So that means rendering less pixels, more CPU cycle available, and we can do rendering faster. And we also have a better text layouting. So that's what is called the fast pass of text in WebKit. I'm not going to look into that in this presentation, but just describe that quickly because I think it's an interesting use case. So what happens is that when you have to lay out text, you have to position each character next to each other. You have very complex table explaining the position of each character depending on what is previous, what is before the character or maybe after, and that can be really complex. And with this fast pass, if you have some simple text that do not require this advanced layout, like Latin 1 text, we just skip all this part and do the rendering faster. This has been used by other browsers. We implemented that in QtWebKit, and that makes the layout of pages way faster, especially if you have lots of text. So now we are going to have a look at a new way of presenting web pages with WebKit. So we are going away from the model you have on your desktop when you interact with the page thanks to a mouse, and you generally have a wheel on the mouse, which is important for scrolling, to something you use on touch devices, on your phone, tablet, or even on something that does not have a mouse, simply a TV or whatever devices people make. And for that, we can present the page differently, we can lay out the page differently, and that's enabling new optimizations. So let's start with the way we render pages today. This is a simplified model of a web browser as you have it on desktop. So what you have here with the dashed rect is the viewport of your browser. So this is what is visible on the screen. And you have the web page, which is here the web page of Qt. And when you are scrolling the page, you are changing the content available in the viewport. Now you can notice this red area that I added. This is to illustrate that you can have elements that are fixed in the viewport, that are not fixed on the page. So if I scroll this red area that is in the page is not moving with the page. It's not moving up. It is staying in the viewport. Now you don't want that on something that is not desktop, that you don't interact with the mouse. you want another model when you use more of the screen. So what happens is that you have a smaller screen. You can render less pixel on the screen. And you don't want to have this big area fixed on top of your small window on your small screen phone screen, because it's going to take half of the space. You have already 200 pixels gone, and you don't use much of the space. So what we do and what you want to do when you have those use cases is to flatten the page and remove those fixed elements from the equation. So this is to illustrate this kind of model. You have the page, and what you do is having a window on top of some like fixed content. So you can see this window as the screen of your mobile phone, and you're moving this window simply by touching and swiping the screen, and you are seeing the area you want. When you have something fixed, it is fixed on the page. It is not fixed on the viewport. So this way you use as much screen space as you can, and you avoid this kind of problems. Now, you know you want that model. How do you implement that? How do you make your application have this kind of interface? This is by using a graphic view and a few additions of Qt 4.7. So first, we are using graphic view, and WebKit is using Qgraphic web view to render the content. So we are talking about Qgraphic web view. And we have this new attribute, this new property in Qt 4.7, which is resize to content. So you can set resize to content to true to say the size of the graphic web view will change with the size of the content. So if the page modify the DOM and the page become bigger, you will have the size of the graphic web view changing in the graphic scene, and you always have the viewport seen as for WebKit as the size of the content. So since WebKit does not see the viewport as the viewport of the window of the screen, it sees the viewport as the size of the page. You never have anything fixed, because what was supposed to be on top of your screen is now on top of the element. What it was supposed to be on the bottom of the screen is just at the end of the item. And now that you have this big flat page in the graphic scene, you want to have this window moving on top of this page, and that's using the graphic view viewport, because graphic view has its own viewport on the scene, and that is what is showing the content of WebKit. So now when you are moving the area visible on screen, you are simply scrolling the graphic view over the graphic item which is in the scene. I think that's quite interesting concept, but also kind of new way of thinking of web pages. I'd be happy to answer questions if somebody have any question about that. Could you?
What do I get if I, in JavaScript, request the screen size?
You are going to get the size of the document. You are not going to get the size of the screen.
And I'm not a web developer, but can't the size of the web page depend on the screen size?
Yes, it does. And we also have attribute to change the size you use to do the layout. So when WebKit layout, it uses the size of the screen by default to layout the content. So you have this, you can take this kind of area when layouting. And I can't remember the name, but on QA page, you can set the size that is supposed to be used by WebKit for the layout. And WebKit will try to layout in this area. And it's like if you add the screen of this surface, but you are not. It's just the way we ask WebKit to do the layout.
Okay, one more question. If the web page thinks it's that big, chances are pretty good, I think, that that I get the whole window just showing part of a scroll pane, of a scrollable area, of a scroll view. Do I get out of there again, or?
I'm not following you there.
Okay, I have scrollable areas in my web page. And if I think I have a big screen, I will probably have a big scrollable areas in there. So if navigation is done through swiping and stuff, if my window, the actual visible part, only shows part of a scrollable area, do I get out of there again?
Yeah, that's a very interesting problem. That's funny you mentioned that. Yeah, you really don't want a scroll area inside scroll area when you are interacting with touch. What you want is to have the scroll area that is as big as the content. And I'm going to mention that it might be the next slide. So it's a very important problem on all these interfaces, and in particular touch. And there are also changes in 4.7 to get out of that, out of there. Yeah, so it was the next slide. Yeah, that is a very common problem. If you have nested scroll area, it's very difficult to deal with that with touch. Think if you have this text and the area you see is like a quarter of this element, so maybe what I select on the mouse with the mouse is what you see on the screen. So if you are scrolling with your finger, you don't know if you are moving in this area or this area. And when you end up at the end of the area and scrolling the next, it is just strange. It does not, it's not natural to use something like that. So what you can do is use a setting to lay out the pages differently. So now you are flattening all the iframes, and all the frames are increase in size to the size of their content, and you don't see any scroll area anymore. You don't have any scroll bar in the page. So with this content, you have this text, you use frame flattening, and you end up with a different layout where WebKit changing the size of everything to get this, this layout without any scroll bar. So now that we have this page without any fixed element on the viewport. So if you scroll, you don't have anything fixed on your screen. You are changing the item. And we don't have any scroll area inside the page itself. So we have one big item without any mobility. We don't have anything that changes with the screen position or with the interaction. All the changes possible are when the page updates something with JavaScript. When you have this model, you can do something very smart with the way you render and do a lot less rendering. And that's what we have with tiling. So the principle is that instead of rendering each frame by going through WebKit and rendering all the pixels, you render a bigger area than what you are currently showing. So here, my viewport is on top of this part, the top left part of my page. So I render a bigger area. I put that in a QPix map. And then when I move the viewport, I don't have to render anything again. I can just take the pix map, put that on screen, and that's just super fast. So the web pages are generally very complex. You have extremely complex text layout, and I mean that's the power of WebKit. You can do very, very advanced layout, and that means also that it takes time to go through all this tree and render everything. So you can have rendering that takes 15 milliseconds or more, and if you want to have a very good performance, you want 60 frames per second. You don't want to do the rendering all the time with complex content. So by using tiling, we render once. It takes 15 milliseconds to render this pix map. And then when we move again, it is just putting the pix map on screen, and it's super fast. Now, what happens when you move from one part to the other? We just render the next part, and then you have 2pixmap. We just show the area on screen, and it's super fast. So there I have 2pixmap in my cache, and as long as I move over those two areas, I don't have any rendering. Now when I go to the next tile, we can drop the previous tile to save memory. And that's just the principle to render the page. You render what you have on screen, you render a bit bigger, those tiles, and then it's super fast to do rendering because you just have to take pixmap and put that on screen. So that was it for the presenting pages differently. That's what you want to consider if you are making something that is not for a desktop computer. If you don't have a mouse, if you don't have anything very precise for the selection, and if you don't have a wheel for the scrolling, you want to consider those models because you can get good performance, and it's probably more natural for the user. Now let's look at something totally different, which is using hardware, using the GPU, I mean, to render some part of web pages. So this is what is called the accelerated compositing path in WebKit. What happened is that some operations are just not fast on the CPU. You have some operations that are fast if you just blend something opaque on top of some opaque content with regular source over. It is just mem copy, and that's super fast on the CPU. Now think about more advanced things like transformation. If you do scale or rotation, that takes some work on the CPU, and that's also not the kind of operation you want to do on the CPU because you are not manipulating each pixel next to each other. You need to take pixels all over the place and throwing the cache all the time. That is not effective. If you want to do scaling, it's also using not direct access. You are taking pixels all over the image, and that is not fast on the CPU because you are misusing the cache. You have the 3D transform. Those are slow because it's simply very complex. You have complex metrics for every operation, every render operation, and yeah, a matrix operation on the CPU, it's a few instructions. On the GPU, it's super fast. So that's the kind of thing you don't want to do on the CPU. And finally, animations. This is more about you want to know when you have an animation, and if you are changing, if your content does not change and you are aware of that, like you have CSS transformation of animation, you want to use some caching. And if you have the GPU and you're already using it, then you can use the GPU as a cache and do the transformation there. And then when you have stuff like alpha blending, that also can be done faster on the GPU with this the animated part. And also in animation, generally you have CSS transform and stuff like that. So what we do is getting help of the GPU, and we take some parts of WebKit. We don't render all WebKits with the GPU. We just take the parts that are supposed to be slow on the CPU, and we get the help of the GPU to do that. So we have two-phase rendering, I would say. You have the first part where you render the content with the CPU, and you put that as a texture. And then you upload the texture on the GPU, and you let the GPU do the heavy work. By the way, we have Noam there, you can stand, who implemented that in WebKit, which is super cool. That we have that in 4.7. And if we have questions, we have the boss there. Here's an example of usage of the GPU to render something. You have the text here, the original text. Now I apply a WebKit 2D transform, which is scale, and I scale the text 3 times. You have this result, and you can see you have high quality anti-aliasing. It's re-rendered using the CPU, and you are not doing any caching. Now if I use a 3D transform, I have the translate Z, even if that does not do anything. We are getting to the 3D path of WebKit, and then it forces the use of accelerated compositing. So what happened here, you can see the text is very different. You have the anti-aliasing that have been scaled, and here you can see the alpha part on the edges that are just scaled. You don't have re-rendering. And what happened is that you take the text as this one, the original one. It is rendered on the CPU, put on the GPU, and then you have this just fairly plain scale done by OpenGL. And that's not necessarily the thing you might think now, yeah, but that is ugly, I want the beautiful one. But now think if you are animating the text, you are scaling it to just explode or get out of the page. You don't want to re-render the full text with full anti-aliasing for every frame, because that's going to take time. So what you have is accelerated compositing, doing the fast operations, and then you have these very fast operations for animations. And I think I'm mentioning translate Z here because you might want to cheat with some content and use this operation to force the caching. If you know that you're moving the item, or this is not going to be re-rendered, but it's very slow to render. That's kind of a cheat to force accelerated compositing. Now, how do you use that? How do you have accelerated compositing with WebKit? It is based on graphic view, and so you have to use QGraphicWebView and not QWebView at the moment. It might change. And if you want to use the GPU, then you have to use OpenGL in the case of Qt, and you can just set a GL viewport on your graphic view. So since you're using GL viewport, well, Qt will do the magic to use the GPU when you're using accelerated compositing. To show a bit how it works, this part when the Qt does the magic, I'm going to show a bit how accelerated compositing is implemented currently on top of graphic view. So you have this very simple case. You have the background in green, which is like a web page. And now you have this red part, which is something you want to scale or animate or anything that goes through accelerated compositing. Now what happened is that this red area become a graphic item in your graphic scene. That become a graphic item that is a child of your graphic view. So we are taking parts of your web page and taking that out of the regular rendering path, and you are taking that into graphic scene. And since those items are rendered as pixmap, so we are not going through the rendering of WebKit again, you can use the GPU. This is done simply by Qt, because if you use a GL viewport, when the pixmap are put on screen, they are using the GPU. They are using OpenGL to do that. So I illustrate you have those two items. You have the web page, which is your regular content, and everything you use accelerated compositing is taken out of this graphic item and is put as a child. And that's why we are requiring graphic view currently. So just some meta accelerated compositing. Since my presentation is done with WebKit, this animation and this 3D transform is using accelerated compositing. So that's my presentation is using QGraphicWebView, and the thing you see moving on screen are just graphic items. Accelerated compositing is great for what is good at. So when you have those transformations that are not good on the CPU. It has also some side effects. You have to think about that, since it may seem strange for web developers that if you scale but you apply a 3D transform, then the rendering is different. I mentioned those side effects. If you scale a pixmap that is already on the GPU, you don't re-render the content, so you will not get, for example, anti-aliasing on subpixels when it's scaled 10 times. And on mobile devices in particular, you can have issues with the uploading time of textures. So if you have a big element that is animated, and you have ARM v7 bigger board, something with a small GPU and not dedicated memory, or even with dedicated memory, the problem is you have a small bus. You have long upload time for this part of the screen to the GPU, and you can see that at the beginning of animations. It might take like 20, 30 milliseconds before the animation starts. It's the time uploading, and the UI is blocked for those 30 milliseconds. That's the time to upload the texture on the GPU. If you have the problem, you can sometimes avoid it by forcing accelerated compositing before the animation. That's an issue on mobile. Now, what if you don't have OpenGL? Since we are using graphic view, everything is based on graphic scene. Just everything works. The metrics are done on the CPU, and all the transforms are done on the CPU. You of course don't have the upload time issue, but you don't get the same speed as if you're using the GPU. And in my case, on my slide, I'm not using the GPU. That's all CPU rendering. So it's still pretty fast on desktop. Of course, I have very, very simple animations. Now we're going to go into the last part, which is about showing a bit of what I do, and hopefully you will be able to do a bit of my job, which is often to have slow web content and find what the hell is going on and why is it slow. So to do that, you have to start profiling WebKit yourself. You should not be afraid of WebKit. It's not like a big black box rendering web pages. It's quite a simple architecture. And if you understand the big parts and understand what is slow, you might be able to find what in the content is slowing down your pages. So we are going to have a look into that. Here I have the main operations of the engines. As you can see, you have many more operations, but like that's the big part of what QtWebKit does. You have the loading of web pages, obviously. And what could happen there is that you have some blocking operation in the loading, and that might be the issue. You don't find that with the profiler, obviously, but if you have loading issues, you can discover that with any I/O profiler. I mean, any profiler showing I/O. Then you have once you have the content loaded, or the content is being loaded and you are about to show something on the screen, you have the layout which kicks in. And the layout is about taking the DOM and making something you can render on screen. So what we have is we have the DOM and we have the render tree, which is another tree inside WebKit. And we are generating the render tree from the DOM, and the render tree describes how the elements are positioned, or they are which size they have, how they are interacting with each other. Like if you have the index, which one is on top. All of that is described as this tree, the render tree. And the layout, this operation of creating the render tree and updating the render tree from the DOM, is quite an expensive operation. So when you have issues of speed and you see that you spend lots of time in layout, even though you are in something that should be rendering heavy, you probably have an issue with your content, and you're updating your content in some special way, in some wrong way. You have rendering, obviously. So the rendering is about finding the value of each pixel on your page. And we have this render tree, which is taken out of the DOM, which is generated from the DOM. And we are going through the render tree to find what to render or to render it. And we are rendering those pixels. And finally, you have JavaScript, which I guess you would expect to see as a big bottleneck. But currently, JavaScript has become so fast that it's very uncommon to see JavaScript as an issue on web pages. You have, if you're using JavaScript Core, V8, or any modern JavaScript engine, you have JIT generating native code for the JavaScript, and it's just amazingly fast. So generally, when you think you have issues in JavaScript, it might simply be that you are rendering too much or you are changing the layout. that is seen by JavaScript because that is JavaScript creating the event, but you have to think that is not JavaScript, that is slow. So now that you know what are the big parts, how do you find what are the issues? My big point here is do not guess what is the issue. Do not try to just change random stuff and hope everything works. You can really profile WebKit, use your favorite profiler, and once you will get familiar with the part of web core. Once you get there, you know where to look when you have some trace, and that's very, very useful knowledge. I mentioned some profiler there. You have Valgrind on Linux, a profile on Linux as well, and that works on devices like MiGo devices. You have Shark on Mac, which I'm gonna go into a bit later. So what you need to do is profile WebKit. You need to understand what part you are on. So maybe go up in the stack and find if you are in the layout or in rendering. And then once you have this knowledge, you can try to find why it is used. So if you find that layout is an issue and you were expecting rendering to be the issue, then you can dig into that and find what is changing the layout so much. So to work with that, we are going to have a look at pages together, and we're going to look at issues they have and how to find the issues and maybe how to solve them. So this is the first example. It's a simple table. You can resize the columns, and then you can scroll the content. And this is taken out from Jira or Bugzilla, I can't remember. But so this has been reported as a slow case of WebKit. The company reporting that, the guy reporting that, said this is slow with WebKit. Please fix WebKit. And the content is really creating the speed issues there. So let's see, what would you expect to be the issue? So what should be a bottleneck in this case? Any idea? I can come back to this. You're shy. Okay. So the bottleneck should be rendering in this case. You are scrolling a page, which means you are just blitzing some pixels. You are showing new content. You have to render that. That means going through the render tree. And you have those, I don't know if you can see, yeah. You have different colors for every line. You have to fill that in memory, render the pixels of the text with anti-aliasing. So that should be the issue. Now, I've profiled this thing. Yeah, it's that one. And this is the profile I got from the application. So start with what we see on top. We have alpha RGB blitz, which is probably positioning the glyph when rendering the text. You have a memfill, which is in this case optimized. And this is just about filling the colors. It's probably a fill rect or something like that. And then we have those very strange trace. We have fast free, fast malloc. So we are allocating a lot, freeing a lot of objects. So we are probably creating tons of objects, deleting tons of objects. And you can also see that we spend lots of time in the interpreter in that case. You probably have a different trace with the JIT, but the idea is that you see WebKit on top, which is doing lots of strange operation. So let's maybe have a look at why we are allocating and deleting so much memory. It is about creating arrays and strings, and we can see changing the document in some way. We have lots of JS node text, lots of stuff are changed. That's just not what you expect from something that should be rendering heavy. You are not supposed to have thousands of new and thousands of delete for each frame. And if we go a bit further, we can see we have some DOM operation. So from that you can see there is something wrong with this content. that is not normal trace. You are not supposed to create thousands of objects and delete thousands of objects every time you have a frame, because you want to do the fast things and you want to be in the rendering as much as possible. So what happened is that this content is not just iframe or div. It is, I mean, it is a div, but it's not just scrolling over the content. The content is generated dynamically from the scroll position. So when I'm in this view, all the area, all the lines, the row that are on the screen are the only one in the DOM. And when I'm scrolling down, what happened is that the developers wanted to be smart and save memory, and they just create new elements at the bottom, remove the old one, and they are changing the DOM all the time. They are removing all those elements from the DOM, adding new elements in the DOM, and that for each frame, because every time you scroll, you have to change the DOM, and that is the bottleneck in this case. You can also, I mean, going from the profile to this conclusion, in this case, I could just look at JavaScript, and then I could understand, oh, this is changing the DOM for every frame, and that was the issue. But if you have more advanced issues, you can use the inspector, and then you have the profiler. We're not going to that, but if you use the profiler on this case, so the profiler you have in WebKit, you will also see that you have add DOM, add node, remove node, and so on the top. This is simply because we are changing the DOM so much. That means layout every time, and that's the slow operation. So how to fix this content? It's very simple. Instead of changing the DOM all the time, you can just reuse what you have. So when you scroll, if you are removing a line, a row, you can just take this element, change the position, and you don't have changed anything. You have the layout for changing the position, but that's just super fast. So next, if you look at our web pages, our web page, it's so. Oh, I guess I play too much with iframes. That's WebKit trunk, not QtWebKit 4.7. So when you have a page that you are scrolling, what would you expect? Again, that should be just rendering. You do not expect the page to change the DOM heavily. I've made a profile before, fortunately, because I would not be able to do it with the bug. And that is the profile as you get from this page. And you can see that there is something common when you have something that performs correctly, is that WebKit is not on the top, it's way down. And you see WebKit is below 1% for the first version. What is heavy is the rendering in this case. So you want to see QtGree on top, because that's a rendering part, and that's what should take time. In the scrolling case, of course. So what we see is simply drawing CG images, which is used by the Windows surface, scrolling direct in image, of course, and you have decoding GIF images, because you have lots of GIF images updating all the time. Some very, very simple stuff. The mag style, I guess it's the scroll bar. Yeah, that's kind of funny. The scroll bar can be quite heavy when you're scrolling. If you have simple content, if the rendering is fast, the scroll bar rendering the scroll bar might be in the trace. And yeah, you have very normal stuff. So what you can see from that, you are seeing what you expect. You expect the rendering to be on top, and you see the rendering in the trace. So you can assume that this content is not causing problem and should be rendered at 60 frames per second without issues. Now the last one is an animation, and this animation is not done properly. Maybe I should. No, yeah, it's not showing the keyframes. So what This animation is done with the WebKit animation, which is good. But instead of using scaling, this animation is changing the size of the font. So for every frame, you are just increasing the size of the font by 1. This is an artificial example, but you can have issues like that if you are changing the text a lot, and you have so you are changing the text, but at the beginning of a page, and you have lots of elements in the page that are depending on the position of the top. So if you are adding a line and changing the width, you might have to relay out everything after this element, and this has been an issue in some use cases. So here, I told you it's a stupid way to animate. You should use WebKit transform, and what you expect is to see layout to be an issue. I'm going to show you what it looks like. So in this case, what I see on top, it's the string to C map of QtGui, which is about finding the glyphs for the text, if I remember correctly. And if you dig into what is calling that, because that's what we want to find, we are in web core. What we are doing, we are layouting. So there you see how you can find these kind of problems. You have a performance problem. You can see the text is on top. You dig into you go up in the stack, and you find that you are in layout, and you are animating. So you are not supposed to be in layout. What you want to be is in rendering again. You want to be the scaling to be slow, to be on top. And so again, when you see this kind of trace, you can find what is the content backward, and then update the content to have some fast operations. That's it for my animations. To conclude, you can get great performance out of QtWebKit. Just look at some setup box using QtWebKit or the N8, the Symbian tree devices. They achieve great animation. They have great interface. They have great applications, and this is made with QtWebKit. But you have to do your C++ correctly. You might have to profile it to do it properly. If you want to use accelerated compositing, you have to use QGraphic WebView. So you have to be careful. You don't get performance for free all the time. It works most of the time, but not all the time. And when you are controlling the content, when you are doing the content for your hybrid application or your web application, you can design a content that is slow. You can make a version you would think that would be fast, but for some reason that cannot be fast. You might have to scale for every frame, and that might be slow. You want to find those issues and fix them in the content, so you get very fast content. And also, don't guess what is the issue, and do not just blame WebKit and create a bug, and we are just going to reject it, and you are going to be frustrated because we don't work improving performance. That's just not the case. You need to profile what you do, and you need to find what is the issue, and it might be in the content. It might not be in WebKit. It might be that we cannot do anything to fix it. And you want to find that and improve your applications to get as fast as you can on mobile devices or small CPUs like Atom or anything you want. That's it. Any question? Come on.
The text layouting, I ran with Qt 4.6 exactly into that in that pitfall. I had a text layouting intensive web application, and I did the profiling that you mentioned today, and
Very cool.
It turned out it was finding the bounding box of texts, which was intensively used. How much did that improve? What I did at that time, I compared it to WebKit on GTK, and it was like 10 times slower or something. Do you have comparisons to other WebKit implementations for Qt 4.7?
I do some comparison with Safari, not much with GTK. What kind of text do you have? Is it Latin 1 text, like simple text?
Yes, it's Latin 1 text.
Yeah, then the new text layout improved that a lot.
Getting in the same region as GTK?
I don't know. I really can't say.
Okay.
We had the issue with like huge pages. You have 1 megabyte of text, and then resizing was slow because then you have to relayout. And like it take 5 seconds to do the readout. That was very slow. And with this patch, it improved very, very. I mean, that was impressive. You could see the thing moving instantly. But
okay.
I can't tell against GTK. I have no idea.
Okay, thank you.
Cool. Thanks you.